Whether you are pulling up a restaurant menu, boarding a flight, sending cryptocurrency, or logging your track and trace details, you rely on a specific square of black and white pixels. Despite its immense utility in our daily lives, this physical grid offers zero visual feedback to the naked human eye. It appears as a chaotic, illegible patch of digital static. Yet that visual chaos is a precision tool that physically bridges our material and digital worlds. It emerged not from Silicon Valley, but from the demands of heavy industry. In 1994, inside a fast-paced Japanese automotive manufacturing plant, production was hitting a critical bottleneck. This is the traditional Universal Product Code, or UPC. It uses a one-dimensional format, reading data through a horizontal sequence of parallel black lines and white spaces. By the 1970s, this design standardized retail inventory tracking across the globe. But by the mid-90s, car manufacturing required far more detailed tracking. A standard 1D barcode maxes out at roughly 20 alphanumeric characters. Furthermore, optical scanners can only read those parallel lines from a specific perpendicular angle. Auto workers found themselves repeatedly pausing the assembly line to scan 5, 6, or even 10 distinct barcodes on a single box of car parts. Each scan required the worker to perfectly align the reader with the label, wasting valuable seconds that compounded into massive production delays. A lead developer at Denso Wave named Masahiro Hara was tasked with a clear objective: engineer a completely new tracking code capable of holding an exponential amount of data and make it readable at high speeds from any direction. Solving this localized factory speed issue required reinventing how optical machines perceive and extract physical data. Hara found his structural inspiration during his lunch break, looking at the alternating black and white stones arranged across the grid of a traditional Go board. He realized he could shift data storage from one dimension, a single line of varying widths, into 2 dimensions, mapping information across an intersecting matrix of pixels. By utilizing both the X and Y axes, the data capacity skyrocketed. A label that previously held 20 characters could now hold several thousand characters within the exact same physical footprint. Adding a second dimension solved the capacity constraint, but it immediately introduced a massive new problem: figuring out how to help a fast-moving laser scanner instantly orient itself within a chaotic, dense grid. Looking at this 3D model, we can systematically deconstruct the quick response code. It separates the random static into specialized anatomical zones. The most prominent features are the finder patterns, the 3 large squares located in the top left, top right, and bottom left corners. Hara's team calculated the least used sequence of alternating black to white areas on printed matter and built these squares to an exact 1:1 to 3:1 ratio. These 3 squares act as fixed lighthouses for the scanner. Because the 4th corner is intentionally left empty, the machine can instantly deduce the top, bottom, left, and right of the label from any angle, solving the factory orientation problem. Next are the alignment and timing patterns, visible as smaller squares with dots in the center, and alternating dotted lines connecting the larger corner beacons. These patterns map the physical topography of the code. If the label is placed on a curved surface, like a cylinder, or scanned at a severe skew, these markers allow the scanner's software to calculate and correct the perspective distortion in real time. Everything left over forms the data modules. These remaining black and white pixels hold the actual payload of data, whether that is alphanumeric text, 8-bit binary code, or kanji characters. A QR code functions as a highly organized composite of navigational beacons wrapped securely around a massive data payload. But the 1990s factory floor was an unforgiving environment. Labels were frequently smudged, ripped, or covered in grease. A single tear through a 1D barcode renders the entire string of data unreadable. To protect the payload, Denso Wave embedded a mathematical solution directly into the grid called Reed-Solomon error correction. Watch what happens in this simulation. By converting the original data into a polynomial expression and embedding backup data points throughout the matrix, you can rip a massive corner off the square, cover it in dirt, and the scanner will still reconstruct the missing information without losing a single character. The highest level of this error correction can restore up to 30% of the damaged code. This is the mechanical reason why modern companies can stamp their corporate logos dead in the center of a QR code without breaking the link. Advanced error correction hardened the QR code from a fragile digital sticker into a practically indestructible physical data vault. Denso Wave achieved global standardization for the code in 2000, yet for over a decade it remained a niche industrial tracking tool. The general public simply didn't carry the dedicated scanning hardware required to read them. The global catalyst arrived in 2017 when Apple's iOS 11 update integrated native QR scanning capability directly into the iPhone camera. When the COVID-19 pandemic hit in 2020 and global industries scrambled to implement touchless infrastructure for menus, payments, and vaccine verification, the global population was already armed with the exact tool required to read the matrix. A brilliant technology requires brilliant engineering, but its ultimate success relies entirely on the widespread, frictionless availability of its required reading hardware. The technology continues to evolve. We now use dynamic QR codes that allow developers to update URLs after the code is printed, micro QR codes designed for incredibly tight spaces on electronic parts, and secure QR codes that carry encrypted private data. What began as a niche automotive inventory tracker to monitor car parts on an assembly line now serves as a foundational link in the modern Internet of Things. It stands as an achievement of structural engineering, a durable, omnidirectional bridge connecting the physical objects we hold to the digital information we need.